single macromolecule. That's what we are going to focus on for the next 3-4 lectures. You will see that it's very fascinating that a single macromolecule can explain so many phenomena associated with polymers. And an important idea behind why single macromolecule behavior is important is related to conformation. So, in this lecture we will focus on molecular conformations, and then in the next 3-4 lectures, this set of lectures, we will look at the aspects associated with single macromolecular behavior. And concepts related to the behavior of single macromolecule will prove us to be very important while describing phenomena such as viscoelasticity, phenomena such as how can protein and DNA molecules pack themselves the way they do in cell, how do they recognize things. So, variety of things are related to single macromolecular phenomena. And so, we will begin by first looking at what do we mean by conformation, and we will see that because of the changes in conformation that a single macromolecule can do, a single macromolecule becomes a statistical object. It has a randomness associated with it. So, we will try to understand concepts related to randomness and statistical properties of a macromolecule. So, let us first look by what do we mean by conformation. So, here even simple molecules like ethane and butane have conformations, and what we mean by that is just the position of different atoms which are there. So, if I were to draw ethane, which is nothing but CH3, CH3, and so when I say the positions of different atoms, what we mean is there is one carbon atom and another carbon atom, and on each of these I have 3 hydrogens. And so now if I look at the positions of the hydrogen atoms on the other carbon, and if I number these, so let us say if I say this is 1, this is 2, this is 3, 4, 5, 6. So, the question that I am asking is how is the relationship in terms of where is position 1 hydrogen located and where is 5 located, and things like that. In fact, if you can think of, if these 3 are the 3 hydrogens on one carbon and these are 3 hydrogens on the other, we are basically saying that look, carbon-carbon bond rotation is possible, and therefore this 1 and 5, are they located like this or is it like this, or so therefore because of the carbon-carbon bond rotation, this ethane molecule can have lots of conformations, infinite basically. So, the angle the way I am showing, so if this I call 0, then 90, 180 and all kinds of angles are possible. And how we can represent this is depicted here, for example, for butane molecule. So, in case of butane molecule, now what we have is 2 of the hydrogens are replaced with CH3. And so, what we have highlighted here is, for example, the position of CH3 with respect to another CH3. And if you look at the energy associated with this molecule, when this carbon-carbon bond rotation keeps on changing, what you can notice is there are some energy maxima and minima. And we know that whenever energy is minimum, those are the conformational states which will be preferred. So, if you look at this butane molecule, we have one conformational state, second conformational state and third. These are where there is the minimum. So, we have this minimum and this minimum. So, you can pause here and look at how the positions of 2 methyl groups are on one carbon, this carbon and this carbon. And of course, when both the methyl groups are closest to each other, the energy is maximum, and therefore that state is unlikely to be obtained. So therefore, the idea behind such an energy diagram So if you look at the methyl groups on carbon atoms in this conformation, both of them are close to each other, and that's energetically not favorable at all, because energy of this conformation is very high. So therefore, based on this such kind of a energy diagram, we can say that which are the three states which are going to be most probable. And what that leads us is in terms of, if I take a snapshot of a butane sample, I will find some of the molecules in conformation state, each of these three. So some molecules will be in one conformation state, some others in another, and in the third one. Or if I am able to pick just one butane molecule, then that butane molecule can flip back and forth between these three. And so a conformational change can happen where a butane molecule is just doing this. Or if I take a random snapshot of several butane molecules, I will see approximately 1/3 in each of the conformational states. So this is the basic idea behind conformational change and CC bond rotation. And if you're not familiar with this diagram, I suggest that you please look at these phrases carefully. What's a potential energy diagram? What do we mean by barrier energy? Because in this case, when conformation has to change, if a conformation is this and it has to flip like this, then a barrier energy has to be crossed. And whenever temperature is higher, it will become easier for this flipping back and forth to happen. So therefore, all of these things, please brush up in terms of activation barrier and potential energy diagrams. So these potential energy diagrams are crucial in terms of explaining why conformational changes happen in polymer. So if we look at polyethylene, we can again just think in terms of a single carbon-carbon bond, and there will be two hydrogen which are there, but then of course this polymer chain continues. So what I have drawn is a single ethylene unit and then chains which are going on, and of course rotation is possible around this carbon-carbon bond. So effectively, if we have capital N bonds and each CC bond can have 3 conformation, a polyethylene molecule with N CC bonds will have 3 to the power N conformations. Now just think what capital N is for polymer, and you will realize how large this 3 to the power N number is. So a single macromolecule, when conformational changes are possible, is an extremely dynamic object where all the different conformations can take place. And if you start thinking of this in terms of each and every CC bond as a single step. So for example, if I say, let's say, draw the first CC bond. Now the next question is, the next CC bond can occupy 3 different states, and I'm just going to use 3 different colors to indicate where the 3 different positions are, and then the next bond again. So if I, let's say, take the blue bond was what is the conformational state. So again I will have 3 options from this blue bond also. So effectively, when I start drawing, I may get a single bond, second bond, third bond, fourth bond, fifth bond. And so what I am drawing is a snapshot of a conformation of a polymer chain. Same polymer in the next instant of time could be first bond, second bond, third bond, fourth bond, and so on. So what we will show is the fact that therefore polymer will be like a random chain where each and every step, because there are thousands and thousands of steps, when I draw the overall polymer chain, it looks like a random chain which keeps on binding over each other, keeps on collapsing over each other. At the same time, when we look at one instant of time and another instant of time, then polymer chain changes its conformation. So that's why it's called a random chain. We also will use the word coil to describe this kind of a macromolecular system. Now, when is conformational change possible? So let's look at the role of conformations and when they are possible. So if we have a crystalline macromolecule or any other crystalline material also, then what we only have are bond vibrations. So in such cases, conformational changes will not be there. Similarly, if we go to an amorphous solid state or a glassy state, then again bond vibrations are there, and maybe we will see this that in glassy state of macromolecules, side groups may be able to rotate. We will see this, for example, that if you have polystyrene and then the side group, which is this benzyl group, can rotate even in glassy state. But the CC bond rotation, which is crucial for the conformational change, is not possible in glassy state. So therefore, as far as conformations are concerned, we don't really have to look at many of these conformational changes as often in glassy or crystalline states. But as far as conformational changes are concerned in the rubbery state or in case of melt state or solution state, they are extremely important. And so clearly you can see that this is associated with temperature. At lower temperature, we will have crystalline or amorphous solid states, and at higher temperature, we will have rubber. Even higher temperature, we will have melt. And of course, if we include a solvent, then that plays a role very similar to temperature by improving the carbon-carbon bond rotational probabilities or making sure that conformational changes are possible. So thermal energy is very crucial to provide energy for crossing the barriers and changing conformations. And conformational change is associated with backbone bond rotation of a macromolecule. In this case, what we have discussed so far is carbon-carbon bond. So here you can think what happens if instead of carbon-carbon bond, single bond, if I have a double bond in the backbone. Will that make the chain less flexible? Instead of a single CC bond, what if I have a benzyl bond? So polyether-ether ketone is a very strong engineering material which is used for aerospace, and it has ether bonds, so CO bonds, and it also has benzyl groups along its backbone. Polyether, ether, and then ketone. What do we expect conformational changes in this kind of a polymer, where there are not as many CC bonds along the backbone? And clearly, yes, your hunch is correct that such kind of polymers, conformational changes will not be as easy, and therefore many of these may not have as coil-like structure, but they may have more rod-like structures. So you can already see that how I am talking about an engineering material which is very strong and hard, and its backbone has a particular degree of flexibility based on conformational change. So using a single macromolecule, we are already talking about mechanical properties of a polymer. And that's why single macromolecule behavior is so important. So just to summarize again, when we look at a single macromolecule, then it will take different conformations from one instant of time to the other. If we look at several macromolecules, then each of the molecule in this ensemble will have a different state, and therefore there is a variation in an ensemble. And so the variables which can be used to describe this polymer chain are as follows. we can look at the chain that we had drawn earlier. So if I start looking at and saying that each and every link here between CC bond is a small vector. So basically my polymer chain is a collection of all these vectors. So I have one vector which I'll call A1, then another vector which I'll call A2, then another vector A3, and so goes going on and on till AN minus 1, AN minus 2, and AN minus 1, and so on. So what I can see is this is a chain. So in this polymer chain also that I had drawn, I can have these bonds everywhere. And so a polymer chain is basically a collection of these links or these bonds, and the collection of all of them is eventually the response of the overall macromolecule. So the variables to describe the polymer chain are the vector which describe the ith bond or the link. Here I am also describing bond as well as link, because soon we will see that instead of describing the polymer behavior in terms of a single bond and groups like CH2 in case of polyethylene or CH2CHCl in terms of PVC and so on, we will start describing polymers more from a model which is like a coil-like material or a chain-like material, because the length of the chain link, the how the link is free to rotate may depend from one polymer to the other, but description of the overall chain can be based on what are called coarse graining methods. We disregard the molecular details but incorporate the interactions of the hydrogens and chlorines and oxygens and carbons into the parameters of our coarse grained model. So therefore, ith link or ith bond can be thought of. There is a length associated with each link, and of course we have ns, total number of bonds. What is the relationship between ns and the molar mass? They are of course linearly proportional to each other. When molar mass is higher, ns is also higher. And a key characteristic of this chain is the end-to-end vector. And so in this case, from the first to the last, this is the end-to-end vector. And what is crucial is the statistical properties and all these conformation changes of macromolecule can be described by this, the fact that R keeps on changing. You can also see already in the random drawing that I had run earlier, you can see that how not only conformation is changing at each and every position, but capital R, the end-to-end vector, also captures the change in the conformation. Other important thing that you can notice is when I drew the chain, it's extremely long, but the end-to-end distance is very small. End-to-end distance, in fact, is much smaller. This is something which is due to the coil-like nature of macromolecule, or because it's a very flexible object. Because the conformational change is easy in case of polymers like polyethylene, generally end-to-end distance will be much smaller than the contour length or the overall length. So if I take two ends of this macromolecule and stretch it and open it completely, then that's the overall length called contour length. So the end-to-end distance is always going to be much less than the contour length. Of course, you can think what happens for a rod-like molecule, in which case this conformational changes are not permitted and polymer is generally in an extended state. So think about it. We will come back to this later on during the course also. So this idea of conformational change and therefore a single macromolecule being a statistical object, we can now start talking it in terms of quantitatively. So the first way to think about statistical property of a single macromolecule is to ask the question, what is the length and direction of the vector connecting the first and last unit on the polymer chain. And we saw that this keeps on changing when conformation changes. And so in terms of definition, this is nothing but summation of all the, so R just a vector sum of all the individual links. And so if I am interested in knowing the distance or the magnitude of this R, then I have to just look at two different conformations and what is the overall distance between end to end. And these brackets here we will use in the course many times. This indicates ensemble average. If I take a bulk sample of polymer, there are 10 to the power 23 macromolecules in it, each of them having different conformations. So when I pose this question as to what is the average end-to-end distance between macromolecules, two ends of macromolecules, I need to do an ensemble average. And so what I need to do is I need to look at all the possibilities of conformations that I had shown earlier. So this is one conformation, this is another conformation. So all such conformations and their averages. And what you can see, the way I have drawn is, if you look at the first link, okay, let me just, so this is the first link, this is the first link. This is the second link and this is the second link. So this is only two conformation. You can already see that the first link orientations are very different in the two cases. So if I start doing dot products of A1 with A1, A1 with A2 and A2, so all of this eventually algebraically you can show, because of the randomness associated with this random chain, that this can simplify as long as we say that the chain can have different conformations at a random scale. So therefore we can describe different types of properties, different types of chain by specifying this end-to-end vector and probability associated with what is a specific instance of conformation of a macromolecule. So effectively what we have is a polymer chain has n bonds and links, and each bond can adopt a different rotational states, and it is equivalent to doing a random walk. So it's like first step, then second step, then third step, fourth step. So therefore it's like a random walk in 3 dimensions, and this is what is the fundamental model theory based on which we get properties of polymers. Remember that a polymer chain cannot overlap on itself, because if there is one link here and then there is second bond and third bond, and it can come back, and after some time again a bond can come close to this, but it cannot overlap. So therefore we have random walk, but it can be a self-avoiding random walk. So this is again theoretical framework to describe properties of macromolecules. Now the second way we can think of the property of a single macromolecule is in terms of orientation correlation. What we are seeking here is, if I draw a random conformation of macromolecule, and if I take any 2 points on it, so let's say I take this point and this point, the question I am asking is, how are the orientations related to each other? If I have a rod-like molecule, then it will be like this. And so if I take any 2 points on that chain, we can see that the orientations are closely related to each other. Because it's a rod-like molecule, conformational changes are not easy, and no bond rotation is possible. So therefore, if I know rotational state of one bond, I know also rotational the orientation state of another bond. Same macromolecule can adopt move like this. But again, if I take a look at two different points, so in a rod-like molecule, there is always correlation between orientation of one point with another point. But that's not the case in case of a flexible macromolecule. So by looking at this orientational correlation, we can think in terms of how flexible is this macromolecule, how easy are conformational changes happening in this macromolecule. And what we can notice here is, if I take 2 points which are close to each other, then what happens is their bonds might be correlated with each other, but when we go far apart, then the correlation drops off. So the question that we can pose is, given an orientation of CC bond at one end, what is the orientation of another bond? So basically what we are saying is, if we look at, let's say, if I start by saying that, I know orientation here, which is my first bond, and I take some other point randomly, and then I am asking this question, what is the relationship between orientation of 1 and orientation of I? And intuitive answer that we can get is, if A1 and AI are close to each other, then they will be correlated. If A1 and AI are far apart from each other, they will not be correlated. But if we have a rod-like molecule, then A1 and AI will always be correlated no matter how far apart they are from each other. So this is done by defining something called a correlation, orientational correlation function, which is again an ensemble average of comparing the orientation of first bond with ith bond. And we would expect this function to decrease as you increase I. So bonds which are closer to each other are correlated, bonds which are further apart are not correlated. So in this lecture, what we have seen is conceptually how conformations makes a macromolecule a dynamic object, in which case conformations keep on changing, and because of this, statistical quantities have to be used to describe a conformational state of a macromolecule. So one other important thing that you need to just remember is that since orientations at two distance point are more random with respect to each other, we can think of a length scale in the macromolecule. Persistence length, persistence of correlation. So 2 points closer to each other, correlation persists. If we go further apart, there is no correlation. So persistence length is a quantification of this idea that orientational correlation goes down when you go far apart in a polymer chain. And we will look at some of these properties of macromolecules and their flexibility in a lecture later on. Thank you.